So, welcome to our to our computer our CSS seminar webinar that organized by the Computational Social Science Lab at the Chinese University of Hong Kong. And today we're very happy to have Dr. Germans substitutions. So
Yeah, perfect.
he's currently a postdoc research associate at the Northeastern University, and his research is very interesting, focused on transparency and fairness of machine learning algorithms used in network science, and with particular interest in mitigating bias in algorithms that model human behavior and social interactions. So Gomez actually obtained his PhD in computer science for sure from the Technical University of Denmark. But his research is that is quite related to social science, as later that you can see. And he focused on using during his PhD study. He focused on using foundation models to study individual socioeconomic and health trajectories. So his work explored the ability of such models to compress multimodal time series and providing even interpretable predictions. So I guess without further ado, let's welcome Gurmis.
Yeah,
Hi,
thank
Gurmis.
you a
Thank
lot.
you, thank you
Yes,
very much. So by the
yes,
way, so for the participants that during the talk, you can always post your questions in the chat board, and later we will try to answer your questions. Okay, thank you.
yes. Thank you very much. Thank you very much for the invitation to give a talk. And yes, today I'm going to talk about the life2vec project, which was published in Nature Computational Sciences around a year ago. And in that work, we proposed a new way to analyze large-scale socioeconomic and health data. We demonstrated how we can do that with the transformer architecture and how we can sort of harness the power of dense representations, as well as how we can then interpret the results of these transformer-based models to get insight into what happens in the population. And the bonus to this paper is also a PhD thesis that was released around 3 months ago, and that you can also find online. And here's the name in case you are interested in learning more. It's a more expanded version about the life2vec. And also, at least in Europe, it got a lot of really interesting coverage, which was not really accurate in most cases and focused a lot on the sort of death prediction part of it. And I hope in this presentation I would show you what was, or I would show you other things that were quite exciting about this work, and not only the death prediction. Just a second. Yes, and for today, I'm gonna go into the data, and then I will do a small crash course on representation learning and natural language processing. And then I will go into the results of our work and what we actually found out during our project. And so the overarching idea for our project was that the fact that life is a very complex phenomena. Events that happen with you today are dependent on your background and the people who you surround yourself with. Different events happen with very different frequency, different kind of time ranges between those events. And all in all, it's a very complex, life is a very complex phenomenon to study. So when we as a social scientist try to infer something about life or quantify something, we usually simplify this very complex signal by asking some specific questions about the problem at hand. And as we do that, we lose a lot of sort of signal that is there in this raw sequences by simplifying the data. So our idea was that what if we can come up with a model that can take this signal as raw as it is and then compress it into some kind of representation to allow us to either study the phenomenon on a global scale or create some kind of predictions or maybe get some kind of comprehensive insight into what actually is happening in the data. And so in our case, we didn't go that far. We didn't create this general purpose model, but we kind of started to do the first steps where, in our case, we worked with two very specific data sets. And we sort of propose a way how we can encode this raw signal, and then we apply the transformer-based models to create the explainable predictions. So I'll start with the data and sort of to give you understanding of how did we get this data. It's important to understand that Denmark as such is a very digitized country. So every time you get income, every time you commit a crime or gamble, or even when you get grades, everything is recorded sort of on the servers. And there is one particular organization that collects all of this data in one place and allows researchers to work with it sort of to answer different kind of questions. And in our case, we pulled two databases. One is labor data and one is health data to sort of create the life trajectories of residents in Denmark. So when it comes to the labor data, just a second. When it comes to the labor data, every time you get an income, it can be a pension, a scholarship, or your salary as a full-time or part-time employee. So there is a record along with the 70 features that specify the amount of income, why did you get it, what kind of job you were doing, what is your company doing, and where do you live at the moment of getting that income. And sort of just by looking at those and arranging them in the sequence, we can already get a very fine-grained understanding of what this person is doing and how their life is evolving. Similarly, we have health data. And when it comes to health, we can see every time that the person goes to the doctor or interact with hospitals, we can see what kind of diagnoses they got, whether it was inpatient or outpatient or emergency case. And we can also see much more than that, but in our research, we focused on those three specific things. And another important thing to know about this data set is that a lot of features in this data set are encoded using some kind of global international classification system. So again, if you look at this system here that's used for industries, you can see that you can specify really specific things, and similarly goes for the occupations. If we further go into the health data, the diagnoses there are encoded in this ICD-10 system. Again, if you look at how this system is structured, you can specify really fine-grained, really detailed thing about what happens with the person. So again, when we combine these two registries and when we reconstruct how the life progresses for each person, we can get really fine-grained information about the progression of this life. And we are also in this unique position to study the progression of trajectories and life outcomes. But now that we have this very complex life trajectories, the question is, how do we analyze that? How do we come up with the models that can sort of collapse all of that into some kind of dense representation? And this is actually where the natural language processing comes into play. So to allow machines and computers to understand text, natural language processing come up with a lot of different solutions. And just to demonstrate you how sort of we arrive at the transformer models or large language models, to for example, convey this simple phrase to the computer, you can do one simple things. For example, you can count how many times each word appears in the sentence. And this is going to be your representation of a sentence that you can then pass to the computer to apply some kind of algorithm. But the problem with this representation is that if I take this vector that I have and I try to reconstruct the sentence, I can reconstruct it in multiple different ways. And you can see that it's quite far away from what I initially had. So on the same thing, on the same sort of topic, is that if you use that representation to represent the sentences, and for example, you want to match people based on their interest, if we use this very simple counting, we would see that Maria and Suzanne are matched together because they use the same word, the word like. But Victor, that prefers apples, and Suzanne, that likes kiwi, wouldn't be matched, even though they both like fruits, right? Because in this kind of representation, the word kiwi and apple are not really the same thing. And what I'm trying to hint at here is that language is also a very complex phenomena, and to sort of convey the meaning of a sentence, you need to account for many, many, many things. And I want to make a point that language, as well as life trajectories, they share a lot of similar aspects or a lot of similar issues, while the field of natural language processing actually came up with two great solutions that we don't really use that much when we analyze life sequences or life trajectories. And those are word representations and large language models. So when we think about word embeddings or word representations, just to sort of give you an idea of what it is that you can kind of take an example of a map where each object has some kind of numerical representation. And in this case, it has longitude and latitude. And since every object has that, now you can reason about similarity between those objects, right? You can take a cosine distances or calculate any kind of distance really to reason how far or how close our objects are. And sort of what people in NLP did is that they decided, well, what if we assign this kind of numbers to words? So we can assign vectors to words where each dimension would have some kind of attribute assigned to it. And if I use this very sort of dummy example, I can create representation of documents, right? By just aggregating the vectors associated with each word. And if I do that, I would actually, if I then compare the representation of documents, I would see that in this example with kiwis and apples, my Victor and Suzanne are going to be matched together because they actually like two words that share some kind of meaning. And there are many, many ways how you can create word embeddings. Creating those manually is a time consuming. It requires you to make a lot of decisions. Your vectors can become really big if you decide to include a lot of different attributes that the word can potentially have. So actually, there are many algorithms that can do it for you based on many, many examples that you provide to them, right? And a lot of those algorithms do it or create word embeddings unsupervised. So they come up with what exactly the dimensions should be. And if you then look at those word embeddings that are created by these unsupervised algorithms, you can see that there is clearly some kind of structure. So either words are grouped in these spaces based on some kind of underlying meaning or function of the word. We can also see that if we are looking at the word embeddings created by this unsupervised or semi-supervised algorithms, we can see that they capture the notion of how big the objects are, or we can use them to sort of reason about analogies, or we can also look at how words evolve through time. So really, word embeddings give us quite interesting way to study language and sort of understand, first of all, how the models understand language and maybe even capture some kind of patterns or some kind of insights about the language. So in a very powerful model that currently in this time can produce the general purpose embeddings as well as give us a really great performance in some kind of prediction tasks are large language models that you probably all of you have heard. And in our project, we used a very specific transformer or large language model, which is called BERT. And in this presentation, I'm mostly going to be mentioning that. And so the idea behind BERT is that you have this sentence that you feed into the model, and then it passes some layers. And first of all, it gives you the embedding of the sentence or of a document, and it also gives you a prediction. And those are two things that we actually want to have when we analyze life trajectories. And just to give you a more sort of deep understanding of how this pipeline works is that you have your sentence here. It then is tokenized. So it's converted to some kind of tokens in your vocabulary. And then each token also get the positional token. So you just specify what is the order of words. And then both are transformed into vectors based on some kind of embedding matrix that was learned during the pre-training. Same goes for the positional tokens. And at the end, your embedding layers produce some kind of aggregated representation of CLS and everything, and so on and so forth. What you do next, you take these aggregated representations and you pass them through the encoder block. In the encoder blocks of transformer models, of LLMs, the vectors are allowed to interact with each other. So the encoder block still gives you one vector per word in your sequence. But at this point, this new vector is going to contain some information about the sequence that it exists in. So in here, in this dumb example, word everything is going to contain some information about word beautiful, for example. And you would do that, you would pass sequence through multiple encoder blocks. It can be 12, it can be 24, 36, and sort of what you get at the end of the BERT encoder is contextual representation of a word. Then you can then pass it to your favorite machine learning model. You can pass it to the decoder. And we can see that using this contextual representation actually boosts the performance of many, many models on many tasks. What is also interesting when it comes to BERT is that the training of such a model is split into two parts. So there is a pre-training where the model is trained on a semi-supervised task, and usually you do it for a really long time. And then when the pre-training is finished, you save the weights of the model, and then you can do the fine-tuning. So you take the weights that you get during the pre-training, and you train it a little bit more on some specific task. And what we again could see that BERT outperformed at that point on many, many tasks that previous model could not solve with such a performance, right? And again, since BERT is a backbone of life2vec, I'm going to go a bit deeper in how it's trained. So on the pre-training, what you actually do is that you pass your sequence. And before you actually pass it, you change some words in the sequence, right? So here I, for example, substituted some aspects of the sequence with some probabilities. And what I do next is that I actually ask the model, okay, so I potentially changed some of the tokens. Can you tell me how the sequence looked originally? And what you do, you provide thousands or millions of sequences. And as you do that, the model learns the underlying structure of the language. It learns how to work with such sequences, and so on and so forth. On the fine-tuning, you add a task-specific decoder. So you take your pre-trained model, you add this another layer that does some very task-specific predictions, and which also sort of collapses the representation of your sequence into one vector. And yes, and as I said already, life2vec is So BERT is the backbone of life2vec because of all these capabilities that we were looking for, the fact that it provides some kind of general purpose understanding of the objects that we use when we, or like words or tokens, and that it provides such a great performance. We thought that that would be interesting to see how we can adapt that idea, but for the life trajectories. And so for now, all my examples were with the language, with the sentences, but as you remember, at our hand, we have this weird sort of tabular representation where we have a number of records per person in a tabular format. So how do we actually go from the tables to text, and how do we train the model on this kind of data? Well, sort of the way to think about that is that every row in your data set can be conveyed, or you can convey the meaning of it using English language, right? But English language also has a lot of structure that we are not particularly, as a social scientists, are interested in, right? So what we decided to do is that what if we can develop our own artificial symbolic language with a very limited vocabulary that we can then use to describe the whatever is happening in the rows of our tables. And then we can operate with that language to describe whatever is happening with the person. So just to demonstrate you how it works is that we have this chronologically sorted records for one person. What we do next is that we look up at the row, we transcribe it into our artificial language. We have words that would represent like your occupation, your income, municipality you live in, and we also had some kind of alternative that would specify the dot for a sentence. We would also extract some kind of positional information, so age and number of days since a specific date, that and also segment, which I will not go too much into. And we would sort of add those tokens into the representation. What we will do next is that we will do that with every record that we have for a person, and we would assemble something that we will call the life sequence. In life sequence, we would also include the sentence that would represent some kind of static, more or less static information about the person, something like sex, birth year, birth month, country of origin. And this, at the end of it, we call the life sequence, and this is actually what we feed into the life2vec model, right? And here you can see the overview of all the variables that we used for our language, and you can see how many words in our artificial language it produces. All in all, we had around 2,000 words that we could use to specify what happens in the life of a person. So yes, and as I said, life2vec is based on BERT, so we pass life sequence through the embedding layer, and then whatever the embedding layer produces, we pass to encoders, and then whatever the encoders produce, we pass through decoders, right? And the pipeline is very similar to BERT. Again, we mask some tokens out. In our sequence, we ask the model to predict what was originally on the places of those tokens. And our data set included around 6 million people. So the model could potentially see this 6 million sequences to train and try to understand how this language operates and what happens there. So the first thing to see for us was, well, after the pre-training, after we did all this masked language modeling and provided the model with the sequences, well, did our model actually learn something? And here you can see how the word embeddings of our language that we developed looks like after the model seen a couple of thousands or millions of sequences. So from the first from the first glimpse, you can see that actually the model did learn at least to separate words into sort of clusters that correspond to different classification systems. So definitely it learned something. So we can also take a closer look. For example, here, one of the most interesting things was to see that the model learned that the concept, or rather words related to income, in this embedding space, they actually form some kind of continuous line. So the model learned to understand this income represents a concept that goes from something really small to something really big, and it learned how to arrange those words and how to work with that. If we look at the cloud of diagnoses, or rather words related to diagnoses, if we just pick a random word in there, we can see that it's going to be surrounded by words from a very similar classification, from the similar class. So fracture of wrist is going to be really close to fracture of arm, or open wound. We can also see a similar thing happening with the jobs. For example, if we pull the token for travel attendants, we can see that the closest concept to it is travel consultant, aviation, and so on and so forth. So from our first analysis, we did think, or we did conclude that our model did learn something. And just to provide you with how we can use the spaces now, is that I can take a word for lowest income, and I can take the word for the highest income, and I can actually create a direction for this concept of income. And what I can do is that I can take all the words in my language now and project onto this axis to see how they how they're related to each other in terms of distances. And I can, yes, important thing to know is that some tokens represent the labor force, and the labor force basically means in what position did you get the income. And we can see that the concepts like student or basic wage earners would be closer to income of the first quantile, while if we move a bit closer to the income of the sort of highest quantile, we can see that it's some kind of managerial role, people. We can also look at the positions. We can see that senior management is closer to the highest income. Servants or fitness instructor are closer to the sort of first quantile income. I'll skip this one here, but you can also draw a more or less obvious directions. For example, here the New York Times has this system that allows you to look up the opposite positions based on some kind of description of the positions. And I decided to look at the chefs, and it seems that the chefs are the opposite of physicists. And I decided to draw a direction from chefs or people who work in the cooking or restaurant industry to physicists, since we had both of those words in our vocabulary. And we kind of can also look at how different tokens or different concepts are existent in relation to those two. And we can see that the physicists seem to be closer to a higher income, to the industry of air and spacecraft, managerial roles, while the people who work in the cooking industry sort of are closer to the lowest income quantile. They are closest to the concept of unspecified pain, and so on and so forth. So you can potentially use this embedding spaces that the transformer learns based on your life trajectories to study how different concepts or socioeconomic or health concepts are related to each other. We also did some robustness studies to see if our model converges to the similar solution if we provide the subsets of data. And basically this curve here means that indeed, if we train life2vec model on 3 non-overlapping data sets, the space that it learns is very closely replicated on each run. So again, it converges to some very robust representation of words. And so what the results of pre-training showed us is that, yes, you can use transformers to sort of analyze or capture structure in data sets that do not really represent one thing. And we can then use this, the embeddings that it learns to maybe study some kind of socioeconomic phenomena. What we did next is to see whether life2vec can actually solve some kind of tasks at hand. So we did some fine-tuning on 3 different tasks. One of those tasks that was mentioned in the media a lot was the early mortality prediction. So the idea was that we provide the sequence to the model and we ask it, well, is the person going to die within the next 4 years after this specific date? And the model could provide either yes, no. One of the biggest issues or challenges here was the fact that while we do have our data sets covers a lot of people, some people move away from Denmark. And so we don't really know their outcome after the 31st December 2015. So we used the positive unlabeled learning framework, which assumes that all the deceased people that we have in data sets are the only truly thing that we know, and all the rest of the samples, we don't really know what exactly happened to them. What it did, what it mostly changed in our case, it was the loss function that we used to fine-tune the model. So it didn't sort of change anything fundamentally when it comes to transformers. So the results after the fine-tuning show us that, well, the life2vec did perform the best. We also tried to apply the recurrent neural networks that use very similar representation of data. Also some simple neural networks, which were multiple times bigger than actually life2vec when it comes to the number of parameters, and we can see that they perform slightly lower. And also the baselines that we use, like logistic regression or something that the insurance companies could use, we could see that they didn't really compare in performance. And here on the right, you can see, I'm not going to go too deep into that, but this is the metric that we use to make those estimates. This is sort of the adjusted matrix correlation coefficient, adjusted for the fact that we use this positive unlabeled learning. We can also look at sort of more fine-grained results of the mortality prediction. So the interesting thing that we found out that the number of events in your sequence or of a person sequence doesn't really change much in terms of prediction. Sort of the sequences with lower number of events have more or less the same performance as for the people who have more than 1,000 tokens in the sequence. The interesting finding was that, well, the more health-related sentences or health-related records you have, the more accurate are your predictions. So people with 18 and more health visits over the 10 years period would have better performance or more accurate estimates than the people who didn't go to the healthcare providers. Another interesting thing that we could see is that if we split, if we look at the results based on the sex and age, we could see that in some cases the predictions were more accurate for females than for males in the same age group. So here as well, here, and we can also clearly see it in the later, in the older people. And we don't really know why that's the case, but the underlying or sort of the hypothesis that we didn't test, but that we had is that in the literature, we know that males are allowed to be a bit more chaotic. They can be more variable in their behavior and the way how they change jobs or the way that they generally are more secure. And so maybe because sequences of females are less variable, it's easier for the model to capture the patterns related to that. But again, this is untested hypothesis. Another thing that we wanted to see whether health data is enough to predict the mortality, or if the labor data actually matters also for the model. And so here you can see the performance if we train life2vec on the full labor and health data. And if we actually remove the health data, if our sequences, if the model is never exposed to health, the performance is still quite good. So labor data, or at least looking at the labor data, the model could identify the people or identify some patterns in there that could predict or be predictors of mortality. Also, even if we feed the partial labor, which excluded most of the variables, we could still see that the life2vec would outbeat the existing some of the existing baselines that we used. As I told you, life2vec, or rather the way how it's trained, also produces the embeddings of your life trajectories, right? And we can also look at the space that is created by these life trajectories. So we could see that when life2vec is trying to predict mortality, it actually arranges sequences into this shoehorn kind of thing, and it places people who are more likely to die on the right side of the space and vice versa on the other side. And we could see, if we zoom in, is that age is one of the most important predictors. So we could see that region 2 has more older people, region 1 here on the other hand has more younger people. We can also see, based on this visualization, that sex is not really used that much, since in both regions the sex is represented more or less equally. Again, this shows us that indeed life2vec did capture something of interest, or something that aligns with the literature at hand. But we could also apply more sophisticated methods to interpret what the model actually learns. And one of the ways to do that is actually use something called TCAF. So if you have this embedding space, you can find direction for different concepts. I'm not sure what I have. Yes, I think I will not go into details of how TCAF are calculated, but the way to think about it is, if in my space, there might be a direction for males, for example. And what it means is that if you project all your embeddings onto this direction and you start walking around this direction, you would meet more and more life trajectories, life sequences belonging to males. And so what TCAF does is that, first of all, it finds these directions for concept in your space. And then it allows you to see that if you randomly pick, for example, 1,000 sequences and move their representation along this concept, in how many of them would the prediction increase? And in our case, if we, for example, walk around the male direction, how many sequences would increase the probability of death? And this is basically what TCAF does. And what we could see is that for the male direction, in all the cases, it's very sensitive. So you can also say that if you are a male, you would generally have higher probability of death. Also, if you have the mental or behavioral diagnosis, in most cases, you would also have the increased probability of death. If you work on some kind of manual job, same effect. There is no effect if you work in some kind of if you are working some kind of high earning position, and so on and so forth. Yes. So another task that we try to sort of implement with life2vec is that we try to see if life2vec can predict the personality traits. In Denmark, there is a research group that randomly picks people from the population and then invites them to play some kind of games or answer some kind of questionnaires. And then based on that, they infer different kind of personality traits of those people. And for our project, we focused on the extroversion facets. And what we asked our model to do is actually to predict what, given the life sequence of a person, what would actually be their answer to 10 questions related to extroversion. So it's a multi-class prediction task. People have seen this kind of statements, and they had one of the 5 choices that they could have made. And so what we asked the model is to predict what would potentially be answers to this kind of questions. And here you can see the results for 10 questions. We use something called quadratic kappa score. Basically, this is a measure that is used for example, ordinal classification for regression, where being wrong by 1 point is not as bad as being wrong by 3 points, and so on and so forth. And we could see that the life2vec model actually was quite good at predicting some of the questions very well, like question number 6, which was connected to social boldness, or question 3 that was connected to self-esteem. It completely failed at question number 7, which was the first thing that I always do in a new place, is to make friends. But all in all, we could see that it still is able to capture some kind of signal in this quite complicated settings. And all in all, this fine-tuning and looking at those 2 tasks allowed us sort of to prove or use it, or we look at it more like a proof of concept, but to say that indeed, if we apply transformers to the life sequences, we can actually use them further for the downstream task, and we can actually use different interpretability methods to kind of gauge or probe the model for why it does or provide certain predictions that we get. And yes, and I think that's sort of it from me. So just to kind of recap, what I've presented during this presentation is a method where that allows us to sort of analyze more or less raw representation of life trajectories, and we've seen how we can form these life trajectories as text, and how we can then further use LLMs to get the explainable predictions. Yes, thank you very much.
Thank you, Simon. Thank you so much. So now we questions from the audience. We take Tony, you want to go first?
Okay, thank you. Wonderful. I couldn't quite follow some of the details, but I do have 3 questions for you. I've written in the chat box. The first one is basically about there's a major difference between analyzing life sequences, trajectories, than analyzing a text. A text is highly structured. You don't have to think about how to pre-process it. But life trajectory came in all sorts of forms, digital, even if it's digital. There must be hundreds of ways to representing them differently. Have you explored whether it matters how you transform the digital inputs, some maybe even in textual natural language format? Whether those things impact the training and the outcome? That is the main part of the first one. And if there's a typical way you have used, what is that exactly? Is it a relational database output, or always a rectangular data matrix, or what? So that's one. The other 2 are more minor, and you can follow that up later.
Yeah. So when it comes to the data representation, so the only thing that we tried is just to transform the rows into the sentences. We didn't look that much into how, we did look into how the size of the vocabulary changes the performance. And of course, if we, just let me see. And of course, if you have more categories and you pre-train it for more time, it gets much better at predictions. The problem is that maybe some things, maybe if I find the slide. Anyways, I don't remember which slide it was, but we decided to keep the vocabulary small for just this project because the training became a bit too complicated and too time consuming. But now in Denmark, I know that there are follow-up projects that try to see how we can use different kind of representations for how we can build sequences or sentences that represent the rows or maybe even the whole life sequence differently, and how that would affect the performance of something like life2vec. For our work, we decided, since it's a proof of concept, we thought that the simplest way to do this sort of this translation from tabular format to just a sentence was to use a very simple vocabulary and very simple sort of framework or pipeline behind it. Now that I know that there is an idea of incorporating the networks. So for example, we can see, or rather in Denmark, they can see who are your families or who you work with, who you studied with. And what they're trying to do now is to see how they can sort of put this graph or network structure along with the sentences, so that the model can at the same time look at the network of people who's around you, as well as the sentences of your life sequence. And when it comes to NLP, natural language processing, they did move from just representing words into some kind of sub-character representation. So if you have word artificial, for example, here, they, in some cases, this sub-character representation can split word artificial into maybe art, and then there's going to be one token, and then facial or something. So definitely natural language processing has a bit more choices and more kind of methods on how they can split words or represent words. But for this for this work, we decided to do really simple things. I hope that answers the question.
So can I rephrase it a little bit? So for each individual, you conceptualize it as a document. And that document has a single line, that's a timeline. And each time point defines a sentence. And that sentence consists of is in turn defined by a piece of information, an event that you as a researcher, you translate it, represent it as a symbolic sentence. So that's why I have the question. This is the sequential way you input every person's maybe a very long thing, and you decide to strategically choose each event to be represented as short as possible, a sentence, symbolic sentence there. My question is, as a sociologist and social scientist, this sentence is nothing but nothing trivial. When we do interviews, for instance, when we record observations, it makes no sense to record interviewees' response to my question in a way that I arbitrarily, so-called arbitrarily reorder things and so on. It's pivotal to do exactly how someone responds to my interviewing question and even in the whole context. So does the translation here necessitate that those contexts are irrelevant? All that relevant is basically the sequence, the timing of having something happening. You see the point. Mechanically, it can conceive as a mechanical process, but in social science, that first part, having the information coded there is the whole story, almost the whole point about data collection in a scientific way. So,
yeah, I mean,
so
I can see your point that, but I would say that even with the questionnaires, at the end of the day, even you record how the people respond to your questionnaires. To analyze that, you would then also make a lot of decisions on how to sort of classify what kind of response it is. And of course, I guess my answer would be, of course, the way how we encode the sequence here would probably, or not probably, but it indeed influence into what exactly the model learns. So yes, in that case, if I understand your question correctly, and here, what we wanted it to learn is that to look at what kind of set of words it has and what kind of information time-wise, position-wise it has, and then sort of in some way sort of try to work with that information. Yeah, I hope it somehow answers the question in a way. Yeah.
Okay, I think I sense the difficulty there, and my initial take here, my first gut reaction is, as a social scientist working with statistical modeling all my life, I would regard this life2vec as a non-parametric statistical model using limited information that has to be structured. Just like in any statistical model, we strip away lots of context, digitizing crucial so-called variables,
Oh, I
always
see.
coding
Yeah,
it as a
okay.
specific number, right? So you are in effect doing it in a much less non-traditional way, not unlike statistical modeling. It's more parametric, non-parametric, I should say, non-parametric, flexible, and still able to let machine learning to recover the underlying patterns, linking all these different cases with highly complex trajectory or event sequences. I would
Yeah.
think of it that way. Then you are not competing in this way. You're not competing with the so-called qualitative research people.
Oh, no, we never said we
You're
did. Yeah.
competing with beating the old guy, beating the statistical modeling guy who use highly structured data input. Now you
Yes,
quickly
I
separate everyone.
I think the way how we imagined it is that something like life2vec can be the first step into the exploratory analysis, right? So our most sort of the interest for us were this embedding spaces where we can look at how things or concept that we predefined or are predefined in the data set, how they are related, and how we can maybe like using something like this simple exercise here, maybe we can identify some kind of, I don't know, relationships that we can further apply more strict modeling, statistical modeling to see whether they actually exist. But I think all in all, the whole framework is more to see and sort of understand. Yes, we do want a good performance, but we also want to sort of find or try to identify some kind of new phenomenon that we cannot do with usual linear regressions or I don't know, like support vector machines, whatever you use to study whatever you're studying there. So yeah, I think that would be sort of the purpose of the whole thing. I think it would be, since this is such a complex model and it does so many complex things, and even people in natural language processing completely don't understand what exactly it captures on some kind of levels. I wouldn't really use it to like say some kind of, to say that, well, if this model figured that there exists this kind of relationship, that it's completely true, but I would rather use it as like a starting point to do more of a confirmatory analysis in the future. I hope that sort of answers it. Yeah.
Since then,
Yeah, since there are no other questions right now, so you can continue.
okay, let me jump to the third question. After training a model, you illustrated, you make predictions by asking it to simulate and like an interview respondent personality, predicting personality. So when you, I know how to do it with GPT, typical GPT modeling, but how do you do that with your case? Do you have to do programming? You need programming to translate it into questions for generating answer to personality items.
Yeah, that's a good question. So what happens there is that we sort of feed this life structure to the pre-trained model, and then we get this contextualized embeddings for each word in our sequence. And what this decoder then returns when we feed this contextualized sequence into it, it actually returns a vector which has 50 dimensions, and so there would be 5 dimensions per question, right? And basically what it returns me is the probability here, for example, is the probability for the first question that the person replies, I strongly disagree, then this dimension would correspond to I strongly, or I disagree, then neutral answer, agree or strongly disagree. And sort of the model is very limited in what it can return. And it returns these numbers for 10 questions. So it's not that we are asking it with some kind of language, but rather the model is constrained to return 50 values that we then use to see, well, what are the replies to this sort of, where is it? So we have, for each person or for each life sequence, we have the vector of 50, and basically returns what kind of probability that the person answers this question, this answer for this question, and then the next 5 would be, okay, so what are the probabilities that the person would answer either of those, and so on and so forth. So it's not really, it doesn't reply as a text. It rather provides this just output, these numbers to us that we can use to sort of understand how close it actually was to predicting the actual thing, if that makes sense.
Yeah. In that case, then I have a follow-up question. You know, people use a GPT to simulate this kind of personality prediction to learn about how machines think, how a model thinks.
Oh yeah.
And I'm thinking of when you develop your project here, it was concurrent with the wide scale availability of large language models, those GPT models, rapid development. What if the symbolic language translation of life trajectory your program can generate? What if you feed it to a GPT model and ask it to learn and then make predictions like what you ask your model to do?
Yes.
Is it in principle doable?
I think there is I've read about the study that would try to use GPT for to predict the locations. So they would basically, they also have a tabular data of how people move around. And what they would do, they would actually translate each of them using like into English sentence. So at 11 p.m. on 28th December, this person went to this cafe, and then the next sentence would be, and at this time and this day, the person went to then this cafe or this place or hospital, and then they would feed this kind of document that is described in English to the ChatGPT. And they actually could see that now. I think the results were that indeed, if you can potentially use the ChatGPT and just like provide these English sentences and kind of get the predictions, and they would be somewhat accurate. I don't remember what was the settings there and what exactly they asked the model to do, but I know that people are trying to sort of convert their tabular data into text, into English language, and see whether they can then use pre-trained models to do the predictions. So this is for sure indeed something that happens already. I think in Denmark, I think there is also there was a project that also used healthcare data where they would translate the codes from ICD-10 system into also English language, and they would be doing something like this person got this type of cancer when they were 25, and they would also assemble the document with this kind of sentences. And I don't remember what was the result of that research, but I know that people are trying to do something like that now. I think in our case, what was good is that we were in full control of the vocabulary that we had. So we also knew what exactly we fed into the model. So with ChatGPT, you don't really know like if it was trained on some kind of corpus of text that claim that the Earth is flat, and like how do you disentangle that if you work with this pre-trained model? So I think in our case we had more, like our model was more restricted, and we knew more about what it seen during pre-training, and kind of we constrained it enough to sort of maybe get somewhat valid results, if that makes sense.
Yeah, it makes sense, but my question is different though. My question is
Okay.
taking your multidimensional representation, learned representation, informed and trained as an input. I take
I
it
see.
as an intelligent, multidimensional new representation of all this complex life trajectory of each individual in your database. Then feed it to a GPT, learn it, and I can verbally ask it, oh, what would happen to this person given this profile? That sort of thing.
I think that would be, that's a nice idea. I think that would be quite interesting project to do, for sure. And I do see why sort of communicating with that kind of model using like spoken language is sort of an interesting and attractive feature. So I think there would be some kind of issues with how to make sure to pass whatever complex structure or whatever complex representation our model learns. Like, I think the issue would be of how to properly like pass that to ChatGPT and just then to ask a question. But I think it's something that for sure with a bit of thinking can be doable and explorable. Yeah, I think at some point we kind of wish sort of played with the idea of talking back to our model. And in our case, because again, we have this very like symbolic language that we use, it's a bit hard, but again, that would be interesting for sure. Yeah.
Okay, thank you. I've taken up a lot of time. Thank you for the
Thank you.
generous sharing.
I actually have a related question. So in terms of ChatGPT and the input of your life sequence, because actually the database that you now you have actually is well structured. So I just think widely that think about that, and now you have a lot of diaries, like individual diaries. So if you have a lot of this kind of things, that's a that they are unstructured for sure. So probably is that possible that we can use it? I guess that it's possible that you can use the ChatGPT to make the data more more structured way from the diaries. So like you can just
Oh,
automatically and then that use your life to vector. I
yeah.
mean that it can just train another vector and so basically means that your input now that another it could be just like diaries, unstructured data.
In theory, yes. I think that can be doable, and you can for sure like translate whatever we have in tables to you can potentially sort of, if you look at it as a diary, you can probably feed that to ChatGPT or to any model that was trained on spoken language. I think not that it was the issue, but like the questions were like, maybe the issues would be that, first of all, you never really know what kind of data the ChatGPT itself was trained on, like, because some of the data that we see was used in earlier ChatGPT 2, we could see that it was very biased, racist, or like, so if you try then to use this model that had this questionable data to analyze life sequences that has a lot of socioeconomic features, like you wouldn't really know what kind of biases would leak into your analysis. I think for me that would be sort of the first question, because I think it's doable. We can take the structured data set, we can very easily transform it into spoken language, and then we can like put it into ChatGPT, and it probably would perform well in many cases. But then there would be some kind of edge cases where it would actually sort of reinforce the biases, or like you would never know what kind of effect there's going to be if so yeah, I think that would be my answer to that question. But it would be again interesting to see what happens there, and whether maybe that's the way to do things for exploratory data analysis. Maybe we don't have to develop our own language, though I do think that restraining the model to some specific things or specific unique words that don't have any subcontext related to spoken language around them, it's kind of beneficial. So it gives you less, or it gives for the model less opportunity to capture some kind of bias. Yeah.
Any other questions from the audience in the room?
Hi, Professor. Thanks for presentation. I have a follow-up question with
Sure.
Professor Liang. Since you and in your slide you have shown that your raw data is a Tableau data, so you transform your Tableau data to textual data like a symbolic sentence. So could you organize your data year by year or month by month for each individuals and consider each time point as a feature, and then in the case of predicting your mortality, would you use the traditional machine learning methods to just what I said, that organize your data into age sequence and then consider each time point for every event in any specific time point as a feature to predict the mortality, and then comparing the difference between uh, uh, the effects of that kind of method and your method, because your raw data is like a very structured tabular data, and then trans transform the data into the unstructured symbolic sentence data, it may be difficult for some reasons and result some bias, as you mentioned before. Yeah.
Yeah, so thank you for the question. Yes, now I'm working on some projects where we try to more or less structure it, not daily, but sort of to constrain it to like yearly. So this is what happened with the person during the year, and this is your yearly overview of the person, and this is the next year, and this is the next year. So first of all, there was the idea to what if we just allow our model to sort of predict next tokens or the next year and then generate this hypothetical sentences for the future, so sort of like hypothetical futures. And the model as it is now, life2vec, wouldn't be able to do that because it was not pre-trained to sort of predict or like generate future sentences. But you can you can update it slightly, like the architecture, to allow it this kind of mechanism. So in theory, you can use some version of life2vec. You can use the LLM to ask it, okay, let's generate. So you have this life trajectory, life sequence for a person. Could you generate 1,000 potential continuations? And then you, in theory, can sort of look at this 1,000 sentences and see what was the most probable outcome. This is the idea that we sort of played around with as well. I think at this point, someone is trying to implement that in Denmark. We also played with the idea of using the survival analysis. So like giving the sequence, actually apply this. At that point, it was computationally super heavy, but we actually did try to predict the exact number of months until the person is gonna die. But at that point, it was like computationally heavy. But for sure, you can update again life2vec. Like the fact that we have the fine-tuning stage, the second stage after the pre-training, allows you to like really sort of to make your model do things that like very different things. And again, I think that like, yeah, so to answer your questions, most of the things are indeed possible. It just requires a small update to how the life2vec operates. So you can potentially generate potential futures, or you can ask, even update the this last layer to predict the time to death or time to the specific event, time to the disease or something like that. It just gets a bit more computationally heavy at that point, but you can still do that. Yeah.
Okay, thank you. Another follow-up question is because your data is based on 6 million people. If I want to generalize this method to another countries, for example, China, we do not have large enough samples. Probably we only have 10,000 samples. So how could this method or your Python package to generalize to another country scenarios?
Yeah. So first of all, like whatever results we have for Denmark, I think it would be a bit unfair to generalize it to other countries, since the context around how Danish society works is a bit different. So I would not generalize the findings that we got to other countries. But the interesting thing that we found while we were training the model is that when the model sees already 10,000 sequences, it doesn't really change the space on this slide. Let me, so it more or less converges to this solution. So the model converges already after seeing 10,000 sequences. So it doesn't need to have 6 million. It doesn't prove, if you have more data, it does improve on, for example, diseases that don't appear that much in the sequences. We could see that, well, they sort of were more this cloud of diagnoses. Somewhere here, there is a cloud of really rare diseases, and it was kind of becoming more nuanced. So, but if you don't use anything like super rare, if something doesn't appear super rare in your data set, I would say that you don't have to use all 6 million people. Like, you can probably get with much, much less people, and it's already converges to some kind of solution. At least in our case, it's somewhat converged to what you've seen, you see now on the screen. So you don't, like, the way how we structured our live sequences, it seems that the model was really fast to identify how things are related to each other. And again, we had only 2,000 tokens. The large language models now have tens of thousands of tokens or words that they're trained on. So again, to answer your question, you don't, I think the amount of data that you have should be fine to train the model.
Okay, thanks for answering.
Okay, any other questions?
Yeah, I do.
Yeah, go ahead.
I have just posed a question in the chat box. I wonder whether you have considered the findings of the Princeton project called Fractal Families Challenge. And it looks like your model may become a contender to revisit what they seem to fail to achieve with previous call for challenge. The previous
we
challenges.
did talk. Yeah,
Yeah.
thank you for the question. We did talk with the Solganic at some point, and I think at the point that our model was ready, or like when we figured out how to model sequences, the challenge was finished at that point, so we couldn't really. I don't think now you can get access to this data. But yeah, I mean, that would be fun to try out, because when we read the description of the challenge, it seemed that it kind of it's very similar, not similar, but it kind of works in the same, like in the same area as we've done. So it would be fun to see that, but I don't think they provide access anymore to people. So yeah.
So they do know your work along this line?
Yes. We did talked about our work, and I talked with him as well about life2vec. I think he included it into his class in February as a topic. So yeah.
Okay. All right. But he still maintains the unpredictability.
Oh yeah. He does. Yes.
It's a new
I
paper
think
at PNAS. I just discovered that.
Yes. Yes. I think my previous supervisor still believes that if we have more data and better models, we still can predict much more. So we'll see how that goes.
Okay.
But I've seen that paper. Yes.
Okay. Good.
Okay, any other questions? If no, so we stop here. So thank you all for coming, and thank you, Gurmas. We hope that we have a chance to invite you to Hong Kong someday. Physically.
That would be fun. Yeah. But thank you very much. Yeah.
Okay, so
thank you.
thank you.
Wonderful.
Thank you all. Yeah, thank you for your wonderful presentation. Yeah.
Thank you.
See you.
Have a good
Bye.
evening.
Yeah.
You too.
Okay.
Thank you. Bye.
Bye-bye.